Double check to make sure.
Social opportunity, homework, homework any day.
Okay. So we are almost done, with all the topics. If you look into these topics here, we are pretty much done. The final exam is here as a reminder, when it's going to be. So this way, we are all reminded every single class that we'll have our final exam on the 12th, which is the first day of final exams, not counting Friday only classes, from 10:15 to 12:15. So make sure make sure that block of time is available. I will check with the lab to see if we can take that test online or not. Okay. Are there any questions about the final exam? It's going to be the same format, except it's 2 hours. It will still be open book and open notes. If we do it online, it will still be open web.
So the same amount of questions, they just work more?
It would be a little bit different. I might change the format to use multiple choice questions, but the multiple choice questions will still have the same trace format. I will give you a trace, and I will just give you a partial trace that is already done, and I might ask you what is going to happen in the next step, or what is wrong with this trace. What is the first line that has a problem? So things like that. But you will get your practice test on I guess the 5th of May. Basically 1 week before the final exam, you will get a practice final as well. So you will know what kind of questions I will ask in the final exam. Any other questions? Now the final exam is 40% of your grade, so that is significant. Okay, it's a significant portion of your grade. So you definitely want to make sure that you don't miss the final exam for one, and then the second thing is you want to get prepared for the final exam. Okay, any questions for all the topics that we have talked about? Yeah.
What would you say is like the best study guide?
The best?
Best study guide to get prepared for this final?
I would say go through the traces that we have done in the class. Mm-hmm. You can also make changes to those programs and see whether you can, understand, whether what this change will do to the program. Changing something from bival to birev, or vice versa. Okay. All right. Well, if there are no questions, the first thing we'll do is just to get refamiliarized with all the concepts that we have introduced at this point. I think with this class, we are also starting to get into abstract data types. Remember when we talked about the projector, the television, LCD screen, and the remote control? So in other words, the remote control is the representation of an abstract data type. Okay, because the way you use your remote control, especially in the case of a television, does not depend on the technology inside the television. It is an abstraction. In other words, to you, all you have to know is where's the power on and where's the power off. Okay, it is independent of the actual technology inside the television. To you, all you have to know is how do I select a new channel? You can either punch in the number or use channel up and channel down. But it has nothing to do with whether it is analog broadcast or digital broadcast. Essentially, it abstracts. It hides all the details that you do not need to know from you. What is the advantage of a remote control? When you change your TV, when you change your television to the next available technology, you don't have to learn anything, okay? Because it works exactly the same way from the perspective of the remote control. Okay, so that's basically what we talked about last time. And it is not this from the programming perspective. This is not a language feature. It is not a feature that is supported by specific programming languages. It is more like a discipline. When you write programs, you have to write programs in a way to isolate changes from the rest of the program. Just only have certain subroutines that will be exposed to the internal construction of a record type. So that's where we ended last time. Let's go ahead and create some examples today that will illustrate all the things that we have talked about so far, and maybe a little bit more than that. So once again, we'll start with a record type, and this time I will have something like this. Okay, b is an integer, and n is also an integer, and record. So this is a very simple record type. it just has two members. These are also called members or fields, depending on which programming language you use. V is a member, N is a member, and both of those are integers. And we'll have another record type here.
But you need a name for the records.
Oh, you're right. I need a name for the record itself. Otherwise, I would not be able to stamp something out of this cookie cutter because it has no name. The cookie cutter itself means a name. I'll call this a node, N-O-D-E, node. And from a node, I can create I'll create a list here. And what a list has in this case is a bunch of nodes. In other words, I can say A is an array of some number of nodes. In this class, I will make it fixed. In some other classes, it does not have to be fixed. So in this class, I'll just make it fixed to maybe 3 nodes. Okay. And F is an integer, U is an integer as well. Okay. And record. So fix the indentations. Are there any questions at this point, of what I'm trying to create here? I'm creating 2 cookie cutters. The first cookie cutter is called node. It's very simple. It only has, each node has 2 members. The first one is called V, the second one is called N. The second record that I'm creating, or the second cookie cutter, is called list. List has, 3 members as well. The first member is by itself an array of 3 nodes. And then the other 2 are just basically integers. So, any questions? Questions? Okay. So I'll go ahead and define subroutines at this point. So the first subroutine I will define is initialize list. And what it needs is passing by reference a list, which is L, and that has to be a list. The first thing it needs to do inside here is L dot F gets a 0, and L dot U gets a -1. And what follows this, is going to be a little bit interesting, because what I'll do is something like this. I need a local variable I, which is an integer. And what I'll do is I'll say I gets 0, for I is less than bar. Okay, L dot A bar -1, and L dot A bracket I dot N gets I plus 1. I gets I plus 1, and while, and then we'll say L dot A bracket bar L dot A bar -1 close bracket dot N gets -1, and define so. Okay, so we'll go ahead and take a look at this subroutine, exactly what is it doing, and why we are doing this too. Are there any questions about the subroutine or the record type at this point? Is there anything that we have not seen before? Well, we haven't seen some of these. I think we have seen it. It's just that some people may have forgotten at this point. Yep, go ahead.
So on line 16, the while statement is that I is less than I bar.
L dot A bar. It's bar L dot A bar again. Well, does that make any sense? That's the first question. Does it make any sense? What is L? L is a parameter. It is passed by reference, and it's passed by reference is a reference to a list. Okay. Does a list have a member called A?
Yes, it's an array.
Okay, and it's an array. So with any array, I can check the number of items in the arrays, and therefore I can use the bar notation. So that's why this still makes sense. We just want to subtract 1 from the number of elements in the member called A of my parameter called L that is passed to init list. So we are basically combining a lot of the concepts that we have seen before, and this is the first time that we basically bundle all of these things together into the same subroutine. And here we should not have any problems with this statement, because starting with L, okay, L is a reference to a list. L.A refers to the member A of a list. And that's, okay, I'm trying to highlight the right portion here. Okay, L.A is an array. With any array, we can definitely do indexing, and that's why we have the open bracket I, close bracket. But each element in the array is a node, and with any node, it has a member called n, because it is right here. And so this is basically, you know, accessing that particular item and make its value I plus 1 compared to what I is at this point. Okay. Are there any questions about this portion here? Yep.
It's kind of a question about arrays in general.
Mm-hmm.
It seems like whenever we're doing a loop or a conditional, we're always testing for bar A bar minus 1, and we're only doing that because the first element is 0. So is there a reason that it's like that it's advantageous that bar A bar represents, that it starts at 0 so that the last number wouldn't be the size of bar A bar?
Minus 1.
Yeah, instead of having it start at 1 so that it would be equivalent?
Yep, there is a reason, but the reason is not going to be obvious until you take cisp300. It has to do with, you know, how items inside an array are organized internally in the memory of a computer. If you want to, you know, just kind of get an idea of what it is, I can just kind of briefly describe that. This will not be in a test. You know, it's just a rationale or explanation of why we start counting from 0. Okay. Okay. So let's just say that, you know, this is a chunk of memory that I'm allocating to an array. Let's say this is an array of 3 integers, just to be simple. Okay. So it makes sense that, you know, this should be a contiguous piece of memory inside the computer system, so that you don't have to allocate one little block here, one little block here, one little block here. So this is contiguous. Okay, and we'll just, you know, randomly say that this is, you know, basically A bracket 0, the first one. This is A bracket 1, and this is A bracket 2. In other words, this is our first element, the second element, and this is our third element. Is that working out so far? So this is how it looks like in the memory of a computer. Don't you think, you know, A bracket 0, the first element, is also at the same place as the starting point of the entire array itself? Because, you know, all 3 combined is the array A. And this is the first element. So does everybody see, you know, how the beginning of the first element is actually the same as the beginning of the entire array? Is that working out so far? In other words, if I want to describe the distance of the first element from the beginning of the entire array, it is at a distance of 0 element from the beginning. Is that working out so far? What about the second element? How far is it away from the beginning of the entire array? It's 1 element away. And the third element is 2 elements away. In other words, the index is basically saying how far is this element away from the beginning of the entire array, but in measuring in units of elements. Is that working out so far? So this makes the calculations a whole lot easier, you know, when you need to calculate the address of this guy and the address of this guy here. And that's the reason why in indexing we start counting from 0 instead of 1. But once again, you know, this is not something that I will ask in the final exam, so don't worry about it. You will see this again in cisp300. Okay, let's go ahead and track down to what this subroutine will do, because it looks kind of obscure. It has all kinds of strange features to it. And to do this, we'll have a stub subroutine. Basically, our stub subroutine is equivalent to what a main subroutine is when you move on to cisp360. We'll have a local variable, which is a list, and either we can call it one way or another. I'll just make it L, and L is a list. We'll go ahead and invoke the subroutine init list. using L to specify L. And define sub, invoke stub. Okay, that's our entire program. How many people actually print out these spreadsheets? Okay. When you print it out, do you want me to use one column for the line number, or do you want to just change the way you print it out so that it includes the row number and the column numbers?
I just, the line numbers are helpful because I don't see the rows.
Okay.
Column numbers.
There's a way to make it print. If you go to, let's see, I think it's going to either format or print here. If you go to print, you can go to options.
I put it in landscape, then I just print it.
Yeah, there's a way to specify to print out the column numbers as well as the row numbers. I think you can go to format, go to page, and you can change the landscape mode pretty easily. Just go to page and change it to landscape, so that's the easy part. But you can also print out the sheet. When you go to the sheet, you can print. Okay, I'm trying to find out where it's supposed to go.
Isn't it back there, column and row headers? Wouldn't that be it?
Is that not on the sheet?
Yeah, right there on the front.
Yeah, column and row.
Yep, there you go. So if you click this and also click this, then when you print it out, it will also include the row number and the column number and also the grid lines.
Yeah.
I can show you what it looks like. I can just go ahead and show you the print preview. So this is what the print preview looks like. So when you look closer, this is what it looks like. It has both the column numbers as well as the row numbers. So this way, if I do it this way, then you don't really need a column for the line numbers anymore because the row number is the line number. Is that working out? Okay. Does everybody understand how to get this to work so that when you print it out, it will also include all these things? Okay. I think that's a pretty useful feature. And we want to get out of here. Turn off page preview. So that means I can save one column here. We can save a little bit of a screen space. Okay. And we'll use a new one to trace it. Okay. Now when we trace this, the first part is going to be really easy. We have comments here, we have line number. For the precondition, there's nothing to say because we don't have any global variables in this case. And then we'll start with line 26. Line 26 doesn't really do much. All it does is to invoke the stub subroutine. And the stub subroutine does not have a return. None of these subroutines have a return at this point. So return line number is more than sufficient. Well, not just sufficient, not more than. Then we go into the stub subroutine starting on line 24. Line 24 is going to invoke init list. So now we have to remember where we're supposed to go back to, as well as the parameter L.
When you invoke stub, didn't you need to create the local variable?
You're right. I forgot about that. Thank you. So I have to create the local variable L in this case. Now the big question is, what does L look like in terms of the columns? Okay, well let's find out what it is. First of all, we have to find out what L is. We are on line 23 at this point because we want to find out, how do we organize the columns for this local variable L. Even though it's a single local variable, it's going to take up quite a few columns. All right, L has three components. It has, three components because we can look up the record list. It has, a component called A. It has a component called F and a component called U. Now, but we want to be sure, how about, what A is, because A by itself is a list of three elements. But each element is not just an integer, each element is a node as well. So A is broken up into three elements, bracket 0, bracket 1, and bracket 2. But each one is also a node, and every node has a V and also has an N element. Okay. So that means L, just the A member itself is going to take up 6 columns. But that's not all. We also have, the element called F, and then the element that we call U. Each one will take up 1 column because they are just numbers. Okay. Now all of these will start with unknown values. So we just use a question mark, and they all start with question marks. That. Okay. Let me just shrink the column so that we can get a better view of the entire thing.
One's good, right?
This works too. Okay. Now if I merge the columns, it will make it a little bit easier to see. This is the first element, the second element, and the third element of the array. The array will take up all 6 columns. The local variable is going to take up all 8 columns. Do we have any questions about the organization of L in terms of the columns that it takes up, and also how the columns are actually used in this case? No questions? This is all good? Really? Okay, so once again, I'll just do it one more time. L itself is going to take up 8 columns. Of the 8 columns, the first 6 columns are, they belong to the first member, which is A, which itself is an array of 3 elements. The first element is going to take up columns D and E, the second one columns F and G, and the third one to take up column H and I. Because each element is also a record, it also has 2 members. It has a member called V, has a member called N, and so on like this. So are we doing okay with this? Okay. Now because this is a local variable, every single column starts with an unknown value. That has to do with it being a local variable. Okay, so now we can officially move on to line 24. So here's line 24. Line 24 is just the invocation of init list. So when we do that, we have to allocate another column for return line number, 1 column for the parameter L, and 1 column for the local variable I. As a local variable, I always starts with an unknown value. L is passed by reference, so in this case, it becomes an alias of all those columns. It will be going from column D all the way up to column K. Okay? And the return line number is whatever is following line 24, which is in this case is line 25. Do we have any questions about how we set up column L to column N? Nope, no questions? Well, I have a question. If I just look at parameter L, which is column M here, it is also known as column D to column K. But how do I look at column D to column K? Because I can look at it as an array of 8 integers, can't I? Well, not exactly, because L has a type associated with it. What is the type of L? It's a list. Okay? It's a list because on line 11 here, I say that L is a pass by reference parameter, but it is a reference to a list. So that basically limits how I can see the columns from column D to column K. I can only look at these columns as a list. Is that working out okay? I cannot use any alternative interpretation of those columns. It has to be interpreted as a list. Is that okay? Kind of. Yep.
So if it's interpreting it as a list, will it only see the part that... Oh, never mind. I didn't realize that the F and U were in the list.
Yep. Yeah, they're all a part of the list. Okay. So now we can move into the subroutine. The subroutine doesn't really do a whole lot of stuff, but it does have a lot of the concepts that we have talked about so far. Okay, so we start with line 13. Line 13 wants to put a 0 into L dot F. What is L? L is this one here. We are not talking about this L. We are talking about this L here, which is column M, which is our parameter. It is also known as column D to column K. So now we know it is actually referring to the L that belongs to the stub subroutine. We want to initialize the member called F to 0, which is column J. So column J is the one that gets initialized to 0. Are there any questions at this point about why column J is the one that is changed? Okay. Then we can look into the other one. We can look into column line 14 of the program. This one is initializing L.U to -1. U is a member of, okay, L is also known as column D to column K, but those columns is basically a list, and a list has a member called U, and in this case, the member U is in column K, so this is the one that is initialized to -1. Any questions about these two lines? They're basically the same kind of thing, just working on different members of the same record. Okay. If there are no questions, we'll move on to line 15. Line 15 is really easy because it's just initializing our local variable I to 0. Then we move on to line 16. And to do that, we need the comments. Line 16 is asking, is I less than var L.A bar -1? Okay, that seems kind of convoluted. So let me just put it here. I is less than var L.A. Well, let's do this part first. What is L.A? What is L? L is column M. Column M is also known as column D to column K. It's a reference, it's an alias of column D to column K. But there's only one way I can interpret column D to column K, which is it is a list. Now, if it is a list, which is a record type list, it has a member called A. The member called A is going from column D to column I, and it is an array of 3 elements. Okay, we have element 0, element 1, and element 2 here. So what do you think is bar L dot A bar?
3.
That's 3. So -1, that will make it 2. Is 0 less than 2?
Yes.
Yes. Okay, so the answer is true. We have to go into the loop here. Line 17 is probably one of the most obscure line of the entire thing, but when you do it one step at a time, it is not that bad. Okay, let's take a look at this line here, and see whether we can track down exactly what it is referring to. Okay, we start with the L here. The L refers to column M, because that's our parameter L. Parameter L refers to column D to column K, which is this particular structure here, which is a list. That list has a member called A. A itself is an array. With any array, I can do indexing, okay? Because if you have an array, you can always specify which element in the array do we want to access. In this case, the element that we want to access is element 0, because I has a value of 0. Okay, so we are now down to this particular item. This item, which is a node, has 2 individual members. One is member I and one is member J. Member V and member N, sorry. One is called V and one is called N. In this case, we just want to modify the one that is called N, which is column E in this case. So we know the column E has to be changed. What are we going to put into it? Yep, we just want to put I plus 1, and I is 0. 0 plus 1 is 1. After line 17, we go to line 18. Line 18 is only going to it's going to increment I by 1. I goes from 0 to 1. Then we go back to line 16. And this is still true because I is now 1. 1 is less than 2 is true. So this time we'll update this guy to a 2. And then we'll go to line 17 again. We increment I from 1 to 2. Sorry?
Line 17.
Oh, okay. I have to shift these down by 1, like that. So here's line 18. Line 18 is incrementing I by 1. Then we go back to line 16. This time, what is the result? It's false. It is false because I is 2. Bar L.A bar -1 is 2 as well. So it is time for us to get out of the loop. We end up on line 20. Line 20 is going to the last element of L.A and initialize its member and the n member of that node to -1. So we are talking about column I in this case. So column I is now initialized to -1. Are we doing okay so far? Yep.
How do you know it's going to the last element?
Say again?
How do you know it's going to the last element?
Because the index inside the square brackets is L dot A bar -1. In other words, it's counting the number of elements -1, which is always the index of the last element. Okay. Are we doing okay so far with this? Okay. And that's it. That's the end of the initialization subroutine. So we are down to line 21 at this point. Line 21 is the end of init list, which means we have to look up the return line number to remind us that we have to go to line 25 next, and then we can deallocate these 3 columns. And now we're back to line 25, and at this point, line 25 is the end of the stub subroutine. I will save this version first because I'm going to use this as an example, and then we'll work on this a little bit more next. Okay. I'll call this list 1 in today's note. Do we have any questions about the subroutine called init list? Let me scroll on the other side so that we can take a look at init list. Let's just stop here and see if there are any questions about this trace. Any questions? No questions? Really? Okay. If there are no questions, I'm going to save this program again, but this time as a different name, because I'm going to make this program a little bit longer. So we'll go ahead and save it as list 2. And I will go ahead and extend the program a little bit here. No.
The hard way.
Yeah, it's okay. We can take a break. Okay, so now we define another subroutine. We'll call this allocate node. Okay. So what it does is it's going to. Okay, let me explain what this is. In terms of the meaning of the code. Okay, a list has 3 nodes in this case. So what we want to be able to do is to allocate a node and then give it to somebody else so that somebody else can use the node for something. But when that node is done using, I want to be able to put it, quote unquote, put it back onto the list. The element F or the member F, which is this one here, is the index of the first free or available node of the list. U is used, okay? It is the index to the first used node in the list. In other words, I'm keeping track of, okay, let me try to explain this in a way that we can all understand what it is. How many people understand what is FAT32 in terms of file systems? Like NTFS versus FAT32? No? Okay.
A little bit, yeah.
A little bit, okay. FAT stands for File Allocation Table. And a basic strategy of a file system is it maintains a list of all the blocks on your hard drive that are available. So when you try to create a file, it will just go through the list and say, okay, give me the next available block, give me the next available block, and so on. So this program is doing something kind of similar to that. But as far as we are concerned, what it means is not as important as the mechanism of doing the trace here. So we'll go ahead and define, allocate node, and all it does is to do something like this. it will need to pass by reference a list. So we have a parameter L again. We don't have it called L, we can call it something else. We can call it X, okay? And it also needs a local variable I so that I can remember what I'm supposed to return. And inside here, I will have to first do a comparison. I will have to check to see if there's anything available on the free list. So if x.f equals to -1, then I just return -1, which is basically saying there are no available nodes at this point, so don't ask me for the next one. If that is not the case, which means x.f is not -1, then I can do something else. Because the first thing I will do is I'll remember what I'm supposed to return, which is x.f. Then what I'll do is, x.n is going to get, now this part is, oops, this is not good. x.a bracket I dot n gets x.a bracket x.a bracket I dot n dot n. Okay? Look at this one here. X dot A, open bracket, close bracket dot n. Does that make any sense? Now before we even run the code, we want to basically just try to figure out whether this can be done or not. Okay, let's look at the right-hand side because the right-hand side is the really obscure part. What is X? Just looking at the code, what is X?
Reference to a list.
It's a reference to a list. Okay, so essentially we can treat it as a list. Does a list have a member called A?
Yes.
And is that an array?
Yes.
If it is an array, can I do indexing with that?
Yes.
I can index into an array. What is an element of that array? It's a node, right? If it is a node, does a node have a member called n? Okay, so if the value of this is proper, this will just give me an integer. Is that working out okay? What can I do with an integer? Can I use an integer as an index? As long as it's the right range, right? Yep. So that's why that can also be, this can also be done because it is basically the same structure. Because what we are doing is we are starting with X, which is a reference to a list. A list has a member called A, which is an array, and any array can be indexed so that we can get to a particular element in the array. In this case, an element of this array is a node. A node has a member called n, so that should be fine as well. Is that okay? I know it looks really obscure, but we should be able to do it. Okay, we'll say and if at this point, and return I, and define sub. Oh, look at that! Just the right number of lines. I'll change that one so we don't have a return in the middle of a conditional statement. Let me change the indentation, and then we'll track it down. We'll find out exactly what it does. And we need more indentations. And now I need to change my program here a little bit. Insert, probably one more insert here. Okay. Local J integer. So we'll say J gets the value of invoke allocate node. And we are using our local variable L to pass to parameter X in the subroutine. Okay. Fortunately, that means some of these line numbers will also have to be changed. So we're starting with line 40, and this part is the same. No, I changed that.
Move step
Yeah, we have to change a lot of the references too, so we need more columns. We need just one more. Because we have local variable j in this case. And then the subroutine starts on line 36. And we have to return to line 37. The rest of the program should still be the same. It's just that this part has to return to line 37 now. I think it is good at this point. Yep.
Are you saving these as different files from the?
Yes, this is list 2
Okay.
instead of list 1. Yep, I learned my lesson. Okay, so I'm not going to trace the program with the initialization, because that part is exactly the same as last time, and that's why I saved as a different name, because I wanted to keep that portion. On line 37, we're going to invoke allocate node, and we want to pass local variable L to parameter X. So that means this time we have to use return info, because alloc node or allocate node is going to return a value. See the return I here? So that's why we need a return info. And with a return info, we typically return to exactly the same line where the invocation is, and we have to specify what else we have to do on that line. In this case, whatever the question mark becomes, we have to put it into local variable j. Is that okay? So what do we do next? Well, we have to pass the parameter. In other words, we have to allocate a column for x, which is our parameter. And there's one more thing to do, because allocate node also has a local variable I, so we need to allocate local variable I as well. Are we doing okay so far with how we allocated those columns? Sort of? Yes? Okay. Now we go into the subroutine called allocate node, starting on line 25.
Forgot to give values to the variables x and y.
Oh, that's right. X is X goes here, I goes here. I is a local variable, starts with an unknown. X is the same as L from the previous invocation. It's an alias of column D and
Will
column.
those become D through L now, since we added another row of J?
No, because J is not a part of L.
Oh.
Yeah, J is on its own, so I should put J here. And then, just to be consistent. Is that okay?
It looks good now.
Hmm?
That looks good now.
Yeah.
It looks good? Okay. I can also do the I can merge columns like these.
Well, how do you know that J is not part of the list of L?
Because J is its own entity. J is a local variable, and it is independent of L. And also, when you look into the definition of a list, it does not have a member called J either. But that that part is actually not relevant, because you can have a member J in a list and still have a local variable called J. They will occupy different columns. Yeah. But in this case, you can see that column L is not a part of L. Column L is not a part of L as a local variable. Okay, so now we can go start execution in the subroutine called allocate node, starting on line 25. Line 25 is checking whether x.f is -1 or not. Okay, what is x? X is a parameter passed by reference. It refers to column D to column K, but you have to look at column D to column K as a list. Well, when you see as a list, this is what you see. Okay. When you see as a list and you want to access member, in this case member F, it has a value of 0. Is that okay? So we are comparing the 0 to -1. Does 0 equal to -1? Nope. So it is false. So now we say that x dot f equals to -1 is false, which means the next line we want to execute is which one? Line 28. Okay, line 28 has one thing to do. We want to put that value into I. Well, since we already know it is 0, we know what we have to do with local variable I. It just has a value of 0. Line 29 is the difficult one, right? This is line 29. It looks really, really obscure. Where do I start? It looks so ugly and so bad. Where do I start?
Go from left to right.
Okay, we have to evaluate the right-hand side first because it's an assignment statement. So that means we always, evaluate the right-hand side first. That means, we have to figure out what is this junk first.
Okay.
So with that junk, where do we start? It looks kind of, really difficult to deal with too.
Innermost parentheses.
Innermost parentheses or brackets. Okay, very good. So the innermost portion is this part here, right? The bracket I is the deepest one. What is I? Do we know what I is?
0.
I has a value of 0. Okay, so we know that part. So the question now is, do we know what this part means? X dot A bracket 0. Well, let's try to figure that out.
It's referring to the array.
It's referring to the array, and which column or which two columns are we referring to when we talk about x dot A bracket I or bracket 0? We're looking at column D and column E. Okay. Does that particular element is it a node?
Yes.
It is a node. Does it have a member called n?
Yes.
And what is the value of the n?
1.
It's 1. It's 1. Okay. Okay. Now, knowing that part is 1, so that means this highlighted portion here just resolved to a single value of 1. Okay. Very good. So now we can look at the outer portion here. So once again, we have x dot A, which is an array. And this whole thing is just 1. Okay. So which two columns are we looking at? F and G. Now, when you look at F and G, is one of those, called N?
Yeah.
And that would be column G. And what value does it have?
2.
A value of 2. All right, cool. So that means the entire right-hand side of the assignment on line 29 resolved to a value of 2. Very good. Where do we put that 2? Well, we put that 2 into whatever column is specified by this junk here. But do we know how to get to that part? What is that? Which column are we talking about?
We're talking about E.
We're talking about column E. So column E now ends up with a value of 2. Okay? And that's the end of this subroutine, end of the conditional statement. We move on to line 31. And on line 31, this is actually incorrect. The code is incorrect, but I'm not going to mess with that. I'm just going to continue the explanation. On line 31, we just have to return the value of I, and the value of I is 0 at this point. So we are returning 0. When we return 0, all we have to do is to copy and paste the return info cell, change the question mark to the value that we are returning, and that's the end of the return statement. Then we move on to line 32. Line 32 is at the end of the entire subroutine, which means we use return info to tell us where we are supposed to go back to. We have to go back to line 37 to continue execution. Then we have no use of these columns anymore, and now it is time to change those. This is X, and that's return info instead of return line number. And now we're back to line 37 to finish up the rest of that line, which means J, which is column L, is going to end up with a value of 0 once we execute that statement. And that's the end. Well, it's not the end of the entire trace, but that's the end of the interesting part of the trace. Do we have any questions about this trace? No questions? Is it nasty? Now, which part of it is nasty? Is it line 29 being nasty, or just the whole thing is kind of? But I just illustrated how you deal with that line, because what you do is you separate it into the right hand side and the left hand side. Okay, you don't even have to bother with the left hand side until you know what the right hand side is going to evaluate to. The right hand side, which is which looks like a big mess because we have all kinds of square brackets and whatnot. You just have to do it from the inside out. Go to the deepest portion of the square brackets, resolve that part, and then you work your way out of this thing. Okay. Are there any questions about this program? List 2. No questions?
Can you go over the right-hand side one more time?
The right-hand side?
Yeah. How that evaluate?
Okay, sure. This is line 29, so we are talking about, I need to look at the row number. So we are looking at row 26 of that. Okay. At that point, I has a value of 0, right? Because according to this trace, I has a value of 0 when we trace line 29 of the code.
So we're only looking at the A bracket I, the innermost. Right
Yeah, we
there.
start with that.
Start with that.
Yeah, we start with that. Trying to figure out, okay, let me see if I can just copy this to sheet 3 and explain that in more detail. Okay, so we are looking at x, okay, we are looking at x dot, x dot A, and then we have the square bracket. Get rid of that first. Okay. Let's do that again. It kept the indentation, which is not what I want. What I'm trying to do here is I'm trying to separate it into individual components, so this way we can work with each individual component. X dot A, and then we have open bracket, X dot A, we have bracket I, close bracket, and then we have a dot N, then we have another close bracket, and then we have another dot N. Okay. Okay, that's what we're dealing with on the right-hand side. Is that right? So the question is, where do we start? If you look at this mess here, where do we start with? We start with the innermost portion of the square brackets, right? Because we cannot deal with the rest until we know this part. Okay, what is I? According to this, I has a value of 0. Okay, so that's the first thing that we resolve, is that this guy is 0. Okay, so now that you know the index is 0, do we know what this is? Okay, X is a list. X is a reference to a list. X dot A refers to the array. It refers to the array A here, which is from column D to column I. Is that okay? And with any array, we can do indexing. In this case, we're doing an indexing because we are using the square bracket. So now we know which part of the array we are looking at. We are basically looking at column D and column E. Column D and column E, one of those is a member called N, and so we know that we are now referring to column E. Column E has a value of 1. Okay, so that means this whole thing evaluates to a value evaluates to 1. Is that okay? So now that you know that part is a 1, and you evaluate the other part, that evaluates to a value of 2.
What did you do with the 1?
The 1 becomes an index into X dot A open bracket 1 close bracket dot N.
That's where I got lost.
Okay, Take it back.
Just rewrite it x dot a bracket 0 close bracket dot n.
Say again?
You can just rewrite it, so it'll be more easier to understand.
Okay, so we can rewrite it as a dot a x dot a open bracket 1 close bracket dot n. Right?
Yeah, that's cool.
Okay, so what is that? Okay, what is x? X is a reference to columns D to K. Column D to K is a list. That list has a member called A. The member A is itself an array of 3 elements. Well, we don't want the entire array. We know which element we want. We know that we want this element to square bracket 1. And then within that element, we also want to access the member called N. And that's why this entire thing resolves to column G, which has a value of 2. Okay? So it really is just one step at a time, but you have to kind of follow the steps, carefully and slowly the first time you do it. But after you have done it a few times, it will get a little faster. Any other questions about this? No questions? Okay, so what is strange about this program? Okay, let me just go back to the source code part. What is strange about this program? What makes it kind of different from all the other programs that we have tracked so far?
So they don't make use of one of the variables? Or one of the elements of the array?
Yeah, well, we have not used it yet. That's correct. But what is the other part? The other part that is interesting is we are using a particular member of a node to serve as an index to get to another node of the same array. Okay? That's a concept called a linked list. It's not you won't see that again until you get to cisp300, which is a data structure class. Okay? But it's a very useful technique because now you can have things to quote unquote point to other things. Okay? Let me show you one thing that will kind of help to illustrate the importance of being able to point to some other things. Okay? Let's look at a binary search tree. Do you guys still remember binary search? Okay, so it's based on a similar concept, okay, a binary search tree. Once again, this will not be in the final exam. I just want to give you, an idea of why do we want to do something like this. Okay, a binary search tree, has a rule, okay? If you look at any node, a node looks like a bubble. It has a value. Okay, let's say this one has a value of 5. I don't really care what is on this side of this bubble. I just know that every node on this side of the bubble, they all have to have values less than 5. I don't know exactly what is on this side, but I know every single node on this side must have values greater than 5. That's what we call a binary search tree. It is similar to the concept of binary search pattern, but it is called a binary search tree. So now the question is, how do we construct a binary search tree? Okay. So when we start, we have an empty tree. Okay, there are no nodes. So let's just look at a list of numbers that we want to put into the binary search tree, and then figure out what or how we're going to put these numbers into the binary search tree. The first one is 5. Now, since the tree was empty before, 5 becomes what we call the root of the entire tree. It becomes the starting point of everything else. Then we have -1. Which side should -1 go? The left-hand side. Since we don't have anything on the left-hand side, we'll make it the first one on the left-hand side. Is that okay? The next one is 2. Which side of 5 should 2 go? Left. And which side of -1 should 2 go? Right? Since there's nothing to the right of -1, I'll make this one the one to the right-hand side. The next one is 7. Which side of 5 should 7 go? The right-hand side. Since 5 does not have anything at this point on its right-hand side, I'll make it the node on the right-hand side. What about 8? Where should 8 go relative to 5? Where should 8 go relative to 7? And what about 6? Where should 6 go relative to 5? Where should 6 go? 6 go relative to 7? Left. Okay. So this is what we call a binary search tree, and it really is kind of interesting because you can input a sequence of numbers that is not sorted, and from this I can use an algorithm to print out these numbers in a sorted fashion. It's called a let's see, this is a binary search tree, so we need a infix order to print out these numbers. Okay. Now, but what is important here is one node has a value, but it also has 2 ways to link to another node. In this case, it has a left-hand side, it also has a right-hand side. Each one will either point to something, either it doesn't have anything to point to, or it points to another node. It also has another interesting property. Let me show you one thing here. Okay, just look at this portion, the portion that is in dotted lines. Does that look like a binary search tree all by itself? Does it play by the same rules? You know, whatever is on the right-hand side is less than, whatever is on the left-hand side, whatever is on the left-hand side is less than, whatever is on the right-hand side is larger than. So it is what we call a self-similar structure. Okay, you take a portion of the entire thing, that smaller portion has to play by exactly the same rules as the big thing. And this is why, you know, we have, you know, programs like that, you know, with a particular member pointing to another node, quote unquote, pointing to another node of, you know, the same type. Okay. Any questions about this particular program? Remember I said this one is actually incorrect. Let me fix it, you know, and we don't have to trace it after we fix it. I just want to give you the correct version. So we'll save this one as list 3. The correct version of this needs to be fixed. The portion that needs to be fixed is here. This is supposed to be x dot f, and not the other node. And of course, the trace is not going to work, you know, up to line 29. So line 29 will be changed. So the 2 does not go here. The 2 will go to the F member, which is column J instead. Column J gets updated to 2. The rest of the program stays the same. Any questions? No questions. Okay, we'll save this. And now we'll switch back to the object-oriented, abstract data type concept. Remember the abstract data type concept that we talked about last time? No? The remote control? The remote control thing? No? Well, let me give you an example like this. How do I represent, if I want to make a program to draw something on the screen, okay, and I just want to represent a pixel, how do I represent a pixel on the screen like this?
It's a coordinate.
Has a coordinate? Okay, so maybe we should create a coordinate first, right? Let's say we are not dealing with 3D here, you know, we're just dealing with a 2-dimensional screen. What is the simplest way to represent a point in 2D?
X1.
XY? Okay, so we'll go ahead and just use XY for that. Okay. That's not hard. Now, how do I represent a pixel on the screen? Well, how do I represent the color of a pixel? RGB is one easy way. You know, for screen purposes, RGB is the right way to do it. When you're printing, you cannot use RGB, or it's not native to printers. Printers like to use CYMK. Can anyone tell me what is CYMK?
That's cyan, yellow, magenta, and
Black. Yeah, because that's how printer works. when you're working with a screen like an LCD screen, it is called an additive process, and that's why you use RGB. Because what is the resulting color of red plus green?
Purple.
Red plus green in terms of an additive process gives you yellow. Okay, if you have a red pixel and next to it is a green pixel and you look at it from really far away, it appears to be yellow. What about red and blue? That's purple. What about G and B, green and blue?
Yellow. Wait. Sorry.
Kind of like in between a green and a blue, right? Okay. But this is not how a printer works. How do you think a printer works? Pigments, right? It sprays pigments onto a sheet of paper. What happens when you spray? Well, first of all, do we have red ink in a inkjet printer? No, we have CYMK because it's a deletive process. It's a removal of color kind of process. So by combining CYMK, you can create the colors that you can see on the printed material. But in this case, for this program, we'll just say RGB is fine. So in order to represent color, we have R, which is just an integer, G, which is an integer, and B, which is an integer. Okay, so this stuff is not too hard. I mean, it also kind of makes sense. Now, how do I represent a pixel?
Coordinate plus the color.
Exactly. Okay, so it has a coordinate. Where on the screen is this pixel? And it also has a color. That's it. Good. What about a circle? How would I represent a circle? Let's say it's a filled circle. How would I represent a circle?
Need a coordinate for the center.
Okay. And what else do I need?
Need the radius.
A radius. And what else?
You need a diameter.
Well, still need the color.
Color.
Because if I'm going to draw something on the screen, I still need the color. Okay. And how about a rectangle?
Wouldn't you also need a degree or an
Need a
angle?
range of X and Y.
Mm-hmm. Okay. There are several ways to do it. Since I already have the representation of coordinate, I can just use two coordinates, right? The opposite corners. That's all I need. So I need corner 1, which is a coordinate. Corner 2, which is a coordinate. So nothing is going to be rotated in this case. These are just really basic shapes. And I still need the color. Okay, this is already enough to illustrate one point that I want to illustrate. If you look at all the things that I want to be able to draw on the screen, what is common to all of these items? The pixel, the circle, and also the rectangle. What is common to all of these?
Coordinate. Color. Coordinate.
The color, okay? But not quite the coordinate, okay? Because the center of a circle is a coordinate, but it's not the same, in terms of the meaning compared to the corner 1 or the corner 2 of a rectangle. Okay, now, if they all have a color, don't you think this is somewhat repetitive? That I have to include a color for every single one of them?
Yeah.
But is there a way so I don't need to do something like that? Is there a way to reorganize, how we define the records so that we don't have to say that a pixel has a color, a circle has a color, and a rectangle has a color?
Wouldn't be there a record which includes those which has the color for all of them?
So you want to basically define a new record type, that has color, and then you just say that a pixel has an element or has a member, like that, and every other shape has a member like that too. Okay, that's not a bad solution, but it's not the solution of object-oriented programming. Okay, so let's forget about programming for the time being, and we look at, let's say, the animal kingdom. Okay, how many people know the animal kingdom? Just a little bit. Okay. When you look at the animal kingdom, how would you describe an insect? Okay, tiny, but qualitatively speaking, how would you describe an insect? What makes an insect and not a spider?
6 legs.
It has 6 legs. Very good. It has antennae. It has compound eyes. There are 3 body segments, and so on and so forth, right? So when someone asks you, how is an insect different from all other animals, these would be your answers. Now, if I want you to describe what is a fly, how would you describe what a fly is? Has wings.
Compound eye.
Well, okay, let me give you 2 options. The first option is like this. A fly has compound eyes, antennae, 6 legs, 3 body segments, blah, 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 and it also has wings, okay? The other way to say it is a fly is an insect, but it also has wings. Which way would you prefer?
Plus the legs.
Yes.
The second one, right? The second one is more concise. Now, why can I do something like that? By saying a fly is an insect, what am I telling you? That it has all the common attributes of an insect. So I don't have to repeat that part. Okay? How about a fruit fly? If I want to describe a fruit fly, what is the best way to describe it? Should I start from the beginning again? It is an animal with 6 legs and blah 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 blah.
Like you could say it's a fly, which you already defined as an insect plus wings.
Mm-hmm.
That germinates in fruit.
And then I just have to describe how a fruit fly is different from all other flies. Okay, how is it specialized to become a fruit fly? Okay, now don't you think it would be nice if we can do that here? Because we can just say that we define something like a drawable shape or just a shape, and put everything that is common into that thing first. And then we can just say that, oh, by the way, a pixel is a shape, a circle is a shape, and a rectangle is also a shape. Don't you think that will help simplify things a little bit? Because even though we can do something like this, what if later on I want to introduce the concept of transparency or the alpha channel into the shapes that I want to draw? Using this method, what do I have to do?
You have to write new ones.
Well, I don't have to write new ones, but I have to add that particular member to every single one. A pixel now needs a new member called transparency. A circle now needs a new member called transparency, and a rectangle now needs a new member called transparency. It's a lot of replication. So it will be nice if I can just concentrate everything that is common to all the shapes that I can draw on the screen. Maybe later on I want to add rotation. Okay? If I want to add rotation, I have to do the same thing again here. Now obviously rotation does not apply to circles, but if I generalize circles to ellipses, then it does apply. Okay? So this is one version of this code. The other version of the code is like this. I will still need to have records, but now I don't use the name record. I use the name class. Okay, so it's a very simple change in terms of words, but it makes a big change in terms of what I can do with those. So I still have coordinate, and the coordinate is still the same thing. It still has x as an integer, y as an integer, and class. We still have color, same thing, R, G, B. So at this point, the word class seems to be synonymous to the name, to the word record. Now we have a new class, okay? I call this shape. And I intentionally leave some of these lines empty because later on I will fill it in. But at this point, I know all shapes have a color. So I'll say, color is a member of a shape, and it is of the type uppercase color. And I'll leave a few blank lines here in the class. Okay. So this is new. Okay, we did not have a record type called shape before. Now we can define class pixel. Okay. But instead of just saying class pixel, we can say class pixel is a shape. And then we only have to specify what a pixel has that a shape does not. And what is that?
Single point.
A single point. Very good. So in this case, we'll say C is a coordinate in class. This is different from last time, because this time I'm separating, the color part to be common to all shapes that I can draw. A pixel is a shape, so that means a pixel automatically has a color. But on top of that, it also has a coordinate, because I want to know where I'm supposed to draw that pixel. I can do the same thing with a circle. A circle is a shape, which means any circle is automatically also a shape, which means it also has a color. But a circle also has a center, which is a coordinate. It also has a radius, which in this case is an integer. And I can do the same thing with a rectangle, with a parallelogram, and all the other shapes that I want to draw. Now, this is really basic. So let's say later on I want to extend the way I can draw these shapes on the screen and introduce transparency. In other words, I want my circle to be half transparent. I want to see the circle itself, but also a little bit of what is behind the circle. Well, where am I supposed to add the transparency member? Should I add it to each one of these? A pixel has a transparency, a circle has a transparency, a rectangle has a transparency, a polygon has a transparency, or is there a better place to put transparency?
Shape class.
The shape class, very good. So now, if I add anything transparency, if I add transparency to the shape class, it is automatically added to all the other classes. Okay? So are you guys seeing, the advantage of being able to say that, oh, this kind of class is also that too, okay? Because, everything that is in shape is automatically in a pixel, and a circle, and a rectangle, and so on and so forth. If I want to introduce rotation, I can just, add this part here, okay? I can say rotation, and now everything has a rotation member. Even the circle one, even though it's not useful in the case of a circle. Is that making any sense? Okay. This is object-oriented programming, because in object-oriented programming, we can say that this particular class is what we call a subclass of another class. So in this case, in terms of the terminology, pixel is a subclass of a shape. And we can also say that a shape is a superclass of pixel. Yep, go ahead.
But a record could also contain another record, so
yes.
How is this different from a record? Because you could have, a record called shape, and then a record called like a pixel, which has the record of shape, and then the record of coordinate still.
Yep, you can still do that. There are additional differences. I know what you're asking. So let me answer those other questions first. Yep.
So for purposes of this class, the words record and class are similar but not the same thing?
You can look at a record as a more limited class.
Okay.
A record is something that cannot be, you cannot say a record is a something, but with a class you can. Yep, you had a question earlier.
Actually, they were both tied into my question.
Okay, so to answer your question, why can't we just, define a record called shape and then have that as a member? Now, do you see shape as a member of a circle? of a pixel. Okay, let me explain it this way. Okay, let's say that we have stop as a subroutine here, and inside the subroutine I have a local variable that is a circle. This. How do I change the transparency of this circle? Now this is the main difference to answer your question and also your question. If we had used a record, then we'll have to say circle dot shape dot transparency equals something, okay, 0, 100%, or whatever. But in this case, because we're using the concept of a class, you can directly access transparency right here, and you can do something like that.
So the difference is that the class inherits all the properties, or the subclass inherits all the properties of the class directly instead
Yes.
of...
It is as if it has those members. But in the case of if you use a record to solve the same problem, then you will need a member to address that particular record that is common to every shape, and the way syntactically it will be different. But conceptually, it also makes a difference because now a shape is a component of a circle instead of a shape is the encompassing description of all the shapes that you can actually draw on the screen. So it makes a difference in both cases, both in terms of the syntax as well as in the context of which one is including which other one. In this case, a shape includes a circle, but not the other way around. It's not a circle includes a shape. So this is the beginning of object-oriented programming. We have about 2 classes to talk about a little bit of object-oriented programming. It won't be in the test. Okay, object-oriented programming is not going to be in the final exam. But unless you guys have questions about concepts that we have talked about so far that will be in the final exam, I can just kind of talk about this a little bit. Yep.
So basically, it's like the class is the overall folder, and the record is a subfolder within the class.
I would use the animal kingdom as an example.
Okay.
Yeah. So you basically look at the general description of species, and then you narrow it down to the subspecies and so on and so forth.